All right, so let's review. So let's just imagine, to get us sort of thinking, let's just imagine we're considering some function, whatever that function may be. And we can draw it in here like so. Let's just call this function f. Now, along this function, or frankly any function, you could pick 2 points along the function. And as is the case with any 2 points, you can always draw a line through them. So in this case, you could imagine a line through the 2 points. Such a line we call a secant line. Take any 2 points along any function, draw the line that goes through those 2 points, call that line a secant line. Okay, now something else that we saw was that if you look at any single point along the function, while your function may appear curved, as you progressively zoom in on that point, what is curved appears flat, and what is flat is a line, and that line could be described as well. That line could be visualized as well. And so if you take any given point on the function, zoom in sufficiently far, you get something straight, and that straight something we're going to call a tangent line. So a line between 2 points on the function, a secant line, a line that is based at a single point along the function, a tangent line. And one of our primary goals of the course at this point has been to develop a method to allow us to determine precisely the slope of a tangent line. Which is almost crazy because when you think about slope, what, change in y over change in x, you need 2 y's and 2 x's to pull that off, which you only have a single point for the tangent line. So let's just start with the slope that we can compute more so directly, and let's use the slope of the secant line then. So let's here remind ourselves of how to find the slope of a secant line. Well, to give us some sort of something to grab onto here, let's just assign labels to the given points. So this particular point is somewhere along the x-axis. Let's just say it's x units along the x-axis. Maybe it's 2 units right, or 5 units right, or 10 units right, but whatever number of units right it is, let's just say it's x units over to the right. Now you know how high this thing is with respect to the function, because if x is where you are left and right, you put that value into the function, and whatever comes out, well, in this case, f of x, would be however tall the function is tall at that point. Now we've also got this other point off to the right of our x. Now how far that is to the right of x is, maybe not clear, I guess, based on the picture, but however far it is, it's some number of units to the right. So however many units to the right that is, let's just call this point x plus h, where the h signifies how far to the right of x this point is located. Because you go x units, you get to the first point, you go h more units, you get to the point over x plus h. And then the question of how high this point is, well, if you're over x plus h, how high up are you? Well, you are up as high as the function would tell you to be when you put in x plus h. So this is just f of x plus h. And now with this in mind, we can determine the slope of our secant line, just like the slope of any line, change in y over change in x. What's the change in the y's? The change in the y's is f of x plus h minus f of x. And what's the change in the x's? That's x plus h minus x. But I mean, think about that for a second, even listen to what was just said. X plus h minus x. X minus x, the x's will cancel, and that's going to leave you with just h. So here is an expression for the slope of our secant line, the purple line, which on some level you could say is cool, but on another level, the whole goal here was to find the slope of the tangent line. The slope of the tangent line, the green line, is not the same as the slope of the purple line. We have an expression for the slope of the purple line. But then you say, well, if we want the slope of the green line, what could we do? Well, instead of looking at the secant line that we originally did, what if we brought our 2 points closer? Rather than our h being large, pushing us way off to the right, what if our h was smaller and we were closer in proximity with our 2 points? Well, you can see what would be here. Let me dash in a line to show this. Well, this secant line with 2 closer points better approximates the slope of the tangent line. Is it the same slope as the tangent line? No, but it's a better approximation than the original purple secant line we drew. If you want a better estimate of the tangent line via another secant line, pick another point that's closer to your point of interest. The closer the 2 points become, the better your estimate becomes. In effect, when those 2 points approach one another, your estimate becomes perfect. When the 2 points approach one another, I mean, we have a method, or at least a tool mathematically that allows us to discuss approach. So if we take a limit, that allows us to assess approach mathematically. And what do we want to be approaching? We want our 2 points to approach one another. We want the point to the right to approach the point on the left. We want the distance between the 2 points to become 0. We want the h, which is a measure of how much further to the right the point to the right was, to be 0. As h approaches 0, the 2 points approach one another. So if we take the limit as h approaches 0 of our slope, we get the slope of the line that results when the 2 points approach one another. And that is precisely the slope of the tangent line. This object, which we talked about sort of extensively the last week that we met in class, is talked about so much in this class that we don't just call it the slope of the tangent line. We actually give it a shorter name. We call it the derivative. Derivative, just a shorthand way to say slope of tangent line. And even one step further, we had a notation to describe the derivative, which is to say if you're dealing with a function f, and you go through the process of taking this limit, the limit as h approaches 0 of f of x plus h minus f of x over h, whatever results from that limit, we call f prime. With a little, a vertical like a half of a quotation mark, an apostrophe. We call it just f prime. That's the way that we sort of articulate that in words. But the long story short is, if you have a particular function, you can run it through this limit to then have an expression for the slopes of its tangent lines. And we actually saw examples of this as we were going through in class, and we saw like if the original function is x squared, you can go through the limit as h approaches 0 of f of x plus h minus f of x over h, and that's going to be a computation. You're going to have to figure out what f of x plus h is. You're going to have to plug x plus h into the original function. In this case, you're going to have to take x plus h times itself. That requires FOILing, but you go through the whole process. You subtract the f of x, you divide by h. You basically work the algebra to get rid of the h in the denominator, because frankly the fact that h is in the denominator puts a 0 in the denominator, which makes no mathematical sense. So the whole goal here, as we're sort of working through such a problem algebraically, is to get the h out of the denominator. And when you do, and then you let h go to 0, you find out that the derivative is 2x. Which is to say, the slope of the tangent line at any point along a parabola is 2 times whatever the x coordinate is. We went through other examples, like if g of x is 1 over x, then whenever we ran through that one, we ran a similar computation, running through the formula, g of x plus h minus g of x over h, taking the limit as h approaches 0, working with the algebra to where we got rid of the h in the denominator, because the h in the denominator was the very thing that made such a statement make no mathematical sense. Once we got rid of the h in the denominator, we plugged in h equals 0, and this one came out to be, if my memory serves me, negative 1 over x squared. The long story short is not, in terms of what's important, is not that you can go through the technique of finding the limit. Although that is important, it's something you definitely need to know how to do. The big realization, conceptually, is that we have a method by which we can find the slope of the tangent line, and that, in and of itself, is a major discovery.